on the previous videos, you were able to learn how to get the base shear, from the given parameters. So today, I'll be teaching how to determine the forces, per per story or on a specified level in the structure. Okay. Okay, but before that, I think I forgot to include in the problem this two. Okay, for example, this one. Uh, for determining the fundamental period T of a building, the CBC gives the following formula. T equals 2 pi square root of summation of Wi delta I squared all over G summation of Fi delta 2. Okay. So this formula represents what? A, defined by method A, B, method B, C, static period, or D, dynamic period. Okay. So far, I have mentioned uh, the formula method A, which is CTH raised to 3/4, right? But on method B, where is the method B? This one for method A. Method B is, I think, okay, so this is now a snippet from NSCP 2015. So this is method B in getting the period of structure. Okay, so we've already used this method A, and now this is method B. Okay, so if you go back to our problem, okay, here's the problem. So this is method B. Okay, what do you notice in that formula? If you remember our previous problem, 2 pi square root of m over k, right? So this one, uh, 2 pi is this one, okay, correct? Then how about mass? Mass is actually this, right? W over g, right? And how about k? Remember the stiffness method, P equals ku, or in, if I rewrite that, F is equal to k delta. Okay, so it involves force and displacement. So that is our stiffness. Okay, so essentially this is just a transformation of this formula. Okay, method B, so which is actually more accurate than method A. Okay, method A is just uh, for faster calculation of period. Okay. But if you prefer a more accurate one, method B is more accurate because it considers the mass and the stiffness of the structure. Okay, so next, by the way, so that means I can to erase this and put in NSCP because it's still a formula applicable in NSCP. Next problem, which of the following buildings has a soft story? So by observation, uh, building 1 and 3, right? Because there's a vertical irregularity here. So this will definitely cause soft story. Okay. And then also this one, soft story. Unlike this building 2, uh, there's no vertical irregularity. Okay. So let's now proceed with problems dealing with application of static force method. Okay, so another problem. There's a three-story hospital in Manila with a special moment resisting steel frame has a calculated design base shear of 444.82 kilonewton. The tributary dead loads of each story, including walls, are given in the following. What is the distributed base shear at the building roof level? So we need to identify the force, right, at this level. Okay, so you need to distribute vertically the base shear. So first, our height is, the typical height is 4.6, therefore the total height is 13.8. Okay, so height is equal to 3 times 4.6. And the base shear V is 444.82. Okay. Period is from method A, CTH raised to 3/4. So since we're using special moment resisting steel, our CT is 0.0853 times 13.8, the height raised to 3/4. So we got 0.6 seconds. So as you know, if your period is less than zero point 0.7 seconds, you do not need to consider FT. So it's equal to 0 as per NSCP 208.5.5. Now the formula for vertical distribution is this. So where do we get this formula? Okay, so this is the formula for vertical distribution. So V minus FT WX HX all over summation of WI HI. Okay. So we'll be using that formula. Okay. So okay, that formula here. Then tabulate. So we have three levels, right? 3, 2, 1. Then input the height per level. So level 1 is 4.6, level 2 is 9.2, and then level 3 is 13.8. And given with the given weight per floor, input that on the table. So we have 1334.46 kilonewton, 1779.28 kilonewton, and then 2224.1 kilonewton, and simply multiply these two values here. So multiply that, you get 18416. Multiply these two, 16369, and this two, 10231. Then find out the summation because we need that here. So summation of WXHX is this. Then plug it here. Okay, now to find the base shear at roof level, so that's F3. So V is 444.82 minus 0 since FT is 0, multiplied by WXHX at that specified level, 1334. Where's that? HX double X, sorry. 18416. So 18416 all over 45016. So you will get F3 is equal to 181.98 kilonewton. So that's how you get the base shear at a specified level. Okay, so next problem, to get the overturning moment. So where's that? So there's a concrete shear wall building. Story shears of each floor are shown. The structure is located in seismic zone 3. So this is hypothetical. Although in Philippines we don't have seismic zone 3. So what is the overturning moment at the base? So you need to simply, by mechanics, no? Simply multiply each force from with their lever arm. Okay, lever arm. Here, okay. So 67 kilonewton multiplied by 3, okay. 80 kilonewton multiplied by 6, here. 102 kilonewton multiplied by 9, okay. And then finally 111 kilonewton multiplied by its height, 12 meters, because the given problem we have a 3-meter typical floor to floor height. Okay, so we the overturning moment is 2931 kilonewton per meter. Okay, so if you draw a free body diagram of the mat foundation, if there is, no, so you're having 2931 kilonewton per kilonewton meter as overturning moment. So if you analyze the mat foundation on a global sense, apply that overturning moment. So it should resist that overturning moment. So next problem. So these are just objective questions. Which of the following elements resist lateral force? 1. Shear wall. 2. Horizontal diaphragm. 3. Moment resisting frame. Or 4. Brace frame. Shear wall is based on our lectures, right? So shear wall is definitely a lateral resisting member, right? Because it resists earthquake. So this is your shear wall. Horizontal diaphragm. Horizontal diaphragms is actually your slab. These are your slab. So if you have um, earthquake force, so you have these are the columns, and then this is the slab or your diaphragm or diaphragm. Okay. How about moment resisting frame? Okay. As I've told you, for a dual system, you have moment resisting frame, which is part of your lateral resisting members. How about this one, brace frame? Of course, you can, uh, if you don't have shear wall, if you're using concrete, sorry, if you are using steel, you can use brace frame as a lateral force resisting. Yeah, okay, so this is also lateral force. Now, for horizontal diaphragm, that means although it participates in the lateral resisting system, it does not necessarily really resist. No, it will not resist. No, it only what? It only transfers. No, diaphragm only transfers your lateral force from this column going up to this column. So that's how the slab um, participates in earthquake. So it only transfer your lateral force. Okay, so that means only 1, 3, and 4 is correct. Okay, how about next problem? The base shear force distribution to the floors above the base should A decrease linearly, B increase linearly, C be uniform at each floor, or D be concentrated. Let's see on the previous problem. What do you notice on this problem here? Is that here? Do you notice in this distribution of lateral force? 67, 80, 102, 111. So in general, the lateral force is increasing linearly. Okay, so you that's how the vertical distribution of base shear. So in general it increases linearly with height above the base. Okay. So if you try to draw a free body diagram of that, so something like this, right? Okay. Next, for the I can say this is NSCP. For the NSCP equation below, what does FT represent? So you already know this, right? And this is force at the roof level, FT. What does FT represent? But the choices are A, stiffness of the top level. So definitely wrong because we're talking about force. B, the fundamental mode response. C, the higher mode response. Or D, the top story drift. Okay, so the answer is actually the higher mode response. So remember what's the criteria in having FT. You only have FT if period is greater than or equal to 0.7 seconds, right? So ibig sabihin, so that means if your structure is has period greater than 0.7 seconds, so which structures are that? Mid-rise to high-rise. So say mid-rise to high-rise. So definitely those buildings, tall buildings, right, uh, will have FT. And so the response of tall buildings, uh, the general response of tall buildings is there's a chance that higher mode may govern. So that's the real um, reason why we include FT, because higher mode uh, can govern or will occur in mid-rise to high-rise or tall buildings. Okay? Because if you try to say low-rise, the behavior of low-rise is say first mode. First mode is something like this, right? So that's the first mode. It could translate here. It could translate like this because earthquake is cyclic, right? But for a tall building, uh, the higher mode could be something like, so if I idealize that as this, a stick, it could be this, it could be this, right? For higher mode, if this is a stick, it mode 2 is say something like so this is mode 1. So mode 2 will be something like this. So this is mode 2. Mode 3 will be something like this. So this is mode 3. So these modes can occur in tall building. Unlike in low-rise building, this the governing mode is mode 1, wherein your sway could either be this or this, right? And higher mode response like this, mode 2, mode 3, so on and so forth, can occur because you're getting taller. No? As you go taller, your sway will not be in general like this. Okay, so that's the real reason of FT. Okay, so next problem. An 11-story, hey, where's that? A 10-story office building with special moment resisting steel frame in zone 4 with near source factor 1 is under study. The total weight of each story is 68,040 kilogram. Determine the base shear using equation 208-4. So this is equation 208-4 under 2010, no? NSCP 2010. It's okay. So I think you already know this. So height is of course 10 story, 10 times the typical floor to floor height, 3.7. Okay, so 37 meters. Period is CTH raised to 3/4 since it's still 0.0853. Then the height is 37 raised to 3/4 is equal to 1.27 seconds. So it's medium rise building already because it's more than 0.7 seconds. And then base shear is CVI over RTW. What do we need? So R is 8.5 because we are in seismic zone 4, right? And T is equal to 1.27 seconds. CV is 0.56. How do I get that? Here, from the table. So under zone 4, your soil type is SC as given in the drawing. Okay, so 0.56 NV. Then weight is equal to 10 story times the typical weight, 68,040 kilogram. So, okay, 680,400 kilogram. Okay, so plug in all the values. So, CV 0.56 times 1 because NV is 1 according to the problem. and then I is 1 because it's just an office building, and then R is 8.5, period is 1.27, and then multiply by the weight. So that's 680,400 kilogram multiplied by 9.81 to convert in kilonewton, right? So you get V equals 346.26 kilonewton. Okay, so this is just the V according to 208-4. Next is, I think this is the last problem. Okay, for now. Okay, so determine the concentrated force at the roof level. Assume base shear is 400,340 kilonewton. Oh, sorry, 400.34 kilonewton. Okay, so using equation for Ft, 0.07 TB. So 0.07 times 1.27 seconds multiplied by the base shear 400.34, that's 35.6 kilonewton. But remember, you should not exceed 0.25 B, right? So what is 0.25 B? 0.25 times 400.34 is 100.085 kilonewton. So did we not exceed? Yeah. Okay, we did not exceed 100.085, so therefore Ft is 35.6 kilonewton. Okay? So okay. So again, so that's all for now for the problem, but I'd like you to remember that we have for how many? Two, one, two, three, four. So four basic design based shear formula. So you now know how to use this formula. So this is 208-8 in 2015. So this is 2015 NSCP. Now this is the so this is the V max. Okay, so this should not exceed this. Okay, and this is the V minimum, and these two, as there we already have problems showing these two formulas. But who will govern among these four formulas? Now, if you have, if this one does not exceed this V max, this will govern. Okay, most likely, this is uh, this if this value is near this and it does not exceed this value, it most likely it will govern. Okay, but if ever this is more than this one, this will definitely govern. Okay, now as a rule of thumb, no, in most low-rise building this formula governs. Okay, in mid-rise to high-rise building this formula governs, because as you notice, for high-rise building your period is high, right? So if you plug in the period in the formula for a large period, your base year will tend to be decreasing because denominator period is in denominator, whereas this one it's not sensitive to the period. Okay, so such like the low rise building. Okay, okay, so I'd like to show you the response spectra here. If you will notice, you can derive actually the formulas earlier of the base shear here. So this is our response spectra. So it's a plot of acceleration versus period. Okay, and what do you notice? 2.5 CA is here. Okay, remember your V max is what? 2.5 CAIW over R. Okay, so CA is here. Okay, I is simply 1 for a typical building. Okay, Now the formula CVI over RTW is this, right here. Okay. So for low-rise building, this region normally governs for low-rise. Okay. Now for mid-rise to high-rise, this region normally governs. So mid-rise to high-rise. Okay. But again, if you notice, there's no R here, no, because this is a design response spectra. What the code did is actually we reduce this response spectra. So I'll just exaggerate the drawing, right? So because we introduced the R, as I've been explaining before. Okay, because remember in the formula V max is 2.5 Ca IW over R. That R introduction is this. So essentially, this response spectra is reduced. Okay, so therefore, your acceleration is also reduced. Okay, so we are using a reduced base shear in our building actually. Okay, because this is so this is, we can say this is an elastic response spectra, while this one is in inelastic response spectra. Therefore, if you are using this response spectra, therefore the code is expecting our building to behave inelastically during the design uh, base shear. If it happens in the lifetime of the building, we can behave inelastically. That's why we can expect cracking, no, on our cross sections. Now also, okay, so this explains this one, right? The reduction of elastic response spectra, right? So if you will read 208.6.5.4, I think this is 2010, no? So it allows, no? The corresponding design base shear is less than the elastic response, right? Elastic response. So this is the elastic response divided by the value of R. Okay, so we are reducing the response spectra by the value of R. So last, for as a last um, no reminder, I compiled also the formulas from NSCP 2015. So I was able to find out some major differences, especially on NA and NB. no? Okay, so if you notice in 2010 we only have this two column in NA, but in 2015 we already have three columns. So please be reminded on that. Okay, for NV 1, 2, 3, 4 in 2015, but in 2010 it's only three columns. So we increase the NA and NB if your distance to fault line is less than 2 kilometers. Unlike in 2010, there's no NA and NB for specific for 2 kilometers. Okay, so that's all for now. Okay, so on the next video, uh, we will be doing the torsional analysis.